Welcome everybody to this talk, and I welcome Piyush and Chaitanya also, who are going to share. So their talk is about code level static checks. So without any further ado, I hand it over to Piyush and Chaitanya. Please go ahead, guys.
Hi everyone, thank you for joining us at Functional Conf 2025. Today we will talk about something that functional programming promises but doesn't always deliver without putting extra effort. That is domain safety and maintainability. I am Piyush Garg and she is Chaitanya Nair, and we are currently working at JustPay as software development engineers. At JustPay we are focusing on making our systems more reliable and safe by leveraging the rich tools and features Haskell provides. We will introduce how compiler level static checks can enforce domain safety and maintainable patterns in functional programming. From years, functional programming has a reputation for safety because of its rich feature set, be it pure functions, immutable data, shown type system, monads, DSL, and many other things. But as system scales, we start seeing some few cracks and few edge cases and unsafe practice creep in the code base growth as the code base grows. To give you a sense of scale, we have over 600K lines of code with hundreds of developers continuously working on it, making changes to it. And in such an environment, it becomes very difficult to maintain the domain integrity of the code. Uh, it becomes difficult to keep the coding standards high up to the mark. At JustPay, we follow a highly agile development and release cycle, which adds to the complexity of ensuring that the best coding practices are followed or not. Like Also making domain knowledge, we have so many domain frameworks and those things and that knowledge available to all the developers, like to scale it across the organization to all the teams, is a big challenge in itself.
So ideally, Justpay is like fintech, and we are more tech-based company, and we think like tech solves like most of our problems, and we want to invest more on the tech, and that is when like we also chose Haskell, and most of our code bases like are in Haskell, and that is why we wanted to think beyond like what we can do with Haskell, and Haskell itself provides us like a safer environment. Like compiler itself is very strong. It is very it takes care of most of the things, but then there are few cases that we also wanted to ensure such that those kind of patterns or those kind of cases will never occur in any of the code bases. And whenever all there are like new people joining us, and we wanted to make sure everyone are on online, and we don't want things to be there on the note or share it as a feedback. Rather than people should be aware of what are the unsafe functions that Haskell has, and how what is the complexity of using it, and we should not use it in certain cases. So all those things, right? Wanted to ensure more systematically. Yeah, this talk is more about like how we overcome like most of our problems using Haskell GHC compiler, and how we enforced using that.
So when working with the Haskell in functional programming, uh, we saw some functional safety issues. First of all, we saw that there are some unsafe function which has in the Haskell libraries. There is one function called head, which takes out the first element of any list. If someone applies it on like empty list, the GHC and Haskell throws compilation runtime error, not the compilation error. So the code will compile fine, but since the data is available at the runtime, it might break the code during the runtime. So such cases we want to avoid at any cost, because we can't really rely on the data, since in the tech there are APIs, and APIs data we can't control from the external sources. And moreover, someone might just write a function which might be non-terminating, like it won't ever terminate. It will just keep on running kind of infinite recursions, since Haskell is based on function calls only. uh, and there are some things we have frameworks and which are written as a like wrappers over the library functions. Suppose there is a function for like some API call, and we are doing some thing, like we are doing some matrix over it, and people are just using the library one, not our ones.
Yeah.
So how could we enforce that?
So we have like our own frameworks, consider like ENVs and all. For example, I'm telling we have like an ENV framework. So we want people to use those framework and not just not the functions from which is available in other libraries in Google, because we have like few rules over that. Sometimes maybe like we have added a logging or a metrics calculator or something, right? So if they use this frameworks, we can also have all those functionalities, but we cannot still restrict people not to use the other functions also. So those kind of things also we wanted to achieve through compiler itself. If the compiler itself say, it would have been more good, right? So that was also one of our motive.
And moreover, since Haskell is purely functional and it provides us ways to write the code in a cleaner and concise way, but there are some things like which needs to be considered. Like there might be some inefficient code, like someone might just use the code like had applied over the fmap over the list. In such a case, what will happen is like the count function will be first applied over each element of the list, and then it will take out the first element. But this is very inefficient. Why to like apply the count n number of times? We can just first set out the first element and then do the count on it. So these kind of codes also, like the Haskell won't throw error by default, but we want it to. So
So it's ideally like whenever we find a pattern, right? We found and we debugged a pattern, and we know that okay, this pattern is going to cause us issues. We don't want to repeat it. So once an issue is identified, it has to be fixed, and it has to be fixed systematically such that these issues will never occur, and no one has to again remember, okay, this is because of that, that is because of that. We don't want anyone to like remember, and we want to fix it systematically. And such any issues is identified as a pattern in the code, we want to fix it so that that will never happen. So that was also one of our biggest motive to do this. And see, we are a payments system, and payments are like very critical, and small issues can have it's in a critical path, right? So we cannot afford any small issues in the code bases. So that's when we wanted, like we have like different states in payment. Consider a transaction, it can be success, fail, or anything. But when we mark something as fail, there has to be reason towards it. You cannot like randomly mark it as fail just because you don't know what is the reason. If there is no validation, you cannot mark it as fail. All those rules, right, compiler does not provide us, right? Like you can do it, like it is a domain rule, it's not like the language rule, right? But we wanted to make this domain also as like a language rule, so that we new people, whoever is joining us and all, they should not like feel okay, I'm touching something like very critical, and what if something misses out or something. Yes, there are reviews and there are things that will take care, but this will be like more good if we can achieve all those things.
to understand these domain safety issues we are talking about, we have done some case studies on like our multiple projects we work on. So let's see one of those and few of those. And the first one is like slow DB query. Like what in one of our test systems, we received an alert that there was one query, DB query, which was running for like so long. It was taking too much time to execute. We on debugging and investigating the issue, we found that it had one. It didn't had any column which is indexed in the database. So as a result, it was taking a lot of time, and the database struggled to deliver the performance it is designed for. Uh, when we were resolving the issue, like we had certain thoughts in our mind, uh, we it raised deeper concerns for us. Like we found this issue now. There might be other cases in the code base like which might already have such things without like the DB query without any index columns. uh, what happens like if these queries can run in if these queries go to the production and like cause issues there. We wanted to automatically detect these issues and like identifies these queries, and even more we wanted to prevent these queries from happening again in future. Like we wanted to prevent developers from writing any new database query which is having non-index columns or like not having any index columns. uh,
So ideally, yeah, this is a pattern that we found, and we wanted to like solve it. Like no more code should do this. Ideally, no one should be able to write code in such a way, because we know this is an issue, and we want to like restrict people from doing that.
Another case study was for the like high CPU. So one of the developers was like making some change, and while he was testing it locally, he observed that his system was lagging, and the code was taking too much of CPU. Like the CPU just blew up. So it took him days to figure out like what change resulted in such high CPU uses. and it turned out to be like some legacy code which was having non-terminating function which no one was using for like years, and now for in his change he had to use that thing, but that was a non-terminating function. So that leads to the infinite recursion, and it was not terminating, so CPU just spike up. But this again raised more questions for us. Like we need to detect such issues at priority, at a, and even before they are introduced in the code, they should not be even introduced in the code itself. So we wanted to prevent any such occurrence in the future, and we wanted to minimize the damage as soon as possible. For instance, you can take this example of this factorial function, and it will explain like how such things can happen in the code. Uh, this factorial function just does a recursive call with the current to number, and the factorial of the recursion over the same number. But ideally, we wanted it to have a number less than the current number. So these can be a small oversight for now. This is a simple example, but when we talk about the scale and when we talk about the bigger how big our code base is, these oversights can be like cause very much.
Yes, we had to when it's a long code base and all, it's hard to debug all these kind of issues, right? So we wanted to make sure we don't allow such code to be there. Yeah, that was also one of our use case. Yeah. So other use cases, something like, yeah, whatever we are telling, right? And consider we have an enum or something, and there can consider from an external system we are getting a response and we have not mapped it correctly, and there is no validation, and just in there are probability in we just put uh, to some state in the default, right? In the default state, there can be some state when we don't do validation, we map it to that. But what if that mapping is incorrect? It has to be an invalid state, right? But what if it's not like mapped correctly? It's a problem. If you see this example, right, there are like four states, and we get a status and we mapped it, and in the default state we just put it as like failed, right? Rather than it should have been invalid. If it was an invalid, there could have been logging or there could have been metrics. We'll take care of the invalid cases. What is it? We can map it accordingly and all those things. But how do we restrict that? We cannot tell that this will not throw any errors, right? And it's all developers knowledge, right? They should be able to do it. But and there are chances that we might miss also, right? Which can be covered in. And what if the scenario never occurs, and one out of like nowhere it occurs, and then we are able to figure out, right? We don't want it to like go catch it at that end, because we are like working in payments, and we don't want anything to be left out, like rather than proper validations, right? If there is no validation, you don't mark it as failure or success, or like there any state that we are interested in, right? Don't mark those states without the actual reason. If you know the reason, yes, you can mark it. Otherwise, you should not mark. All those restrictions also we wanted to like incorporate. So that is also like one of the motivation.
Another case we had was like we saw some unmasked data in the loss in our debugging system. On seeing the loss, we were sure like someone had just and put a debug log with the just adding the show on the Haskell type. So for those who are new to the Haskell, what does show function does is like it takes any Haskell type and it converts it to its string representation. But this string representation, how it is the Haskell type is converted to the string is like depends from the like how the user has implemented or the developer has implemented. So for the library functions, we could not do anything like however they have implemented, we have to use that way only. But since the developers or like new joinees might use the show for like debugging and then later forget to remove it, we wanted something to like automatically detect such case and don't even allow it in the code base. And we've only but the show function has some characteristics for like might have some good use cases as well for us, like some type might actually do something for like show, like if it is a enum type we might want to have the show on it. So we need something to selectively prevent this, like selectively only disable the show on the like if it is on a Haskell type during the logging, because that is what's causing the issue, not the like show function itself. It was the usage of show inside the logging. So
So yeah, logging, it might make sometimes double stringified, and sometimes it's hard. The logging pipeline might break or something. We don't want that to happen, but we don't want to restrict this over also on a particular type we want to restrict, or on a particular thing we want to restrict, because on a string and show on a string, it's an ops, right? We don't want to do that also. So it's just like we wanted to restrict a few things on a few types and on a few functions, particularly maybe log or something. Yeah, that is when we wanted to ideally do, because here, for example, if you see that log value would make it double stringified, and if we are having some like pipeline built on top of it, right, it might not like work, or that there can be like issues. And when we know we can solve this using like rules, or when we know the issue, right, we wanted to solve it in the code level and not in that consumer level. So that is also like one of the use case we thought. Yeah, that is also like one of the major use cases.
Seeing all these like issues and these case studies, we kept coming back to the same idea, like how can we systematically prevent and identify these issues. We did not wanted to repeat any of these issues, like anything we have seen as an issue we did not wanted to repeat in the future. We wanted a solution which is scalable to all the repos we have or all the applications we have. This huge code base, scaling it to huge code base is like very difficult, because uh, no one can like manually go and see like how where that these functions are used. So we needed something to be automated, some automatic solution for this. And we did not wanted any performance impact also, like we could have considered some runtime solutions, like we could have just check add a validation at the runtime, but no, that won't give us the thing which we desire, because it might have some performance impact, and it will again be catched at a runtime only. So we did not wanted that. Also, we wanted to minimize the human intervention, because humans can make mistakes but machines can't. Like if they are programmed to do something, they will do that thing in exactly same way, no matter how many times you do the iteration. With humans, that is not the case. Like if a human is catching one error right now, in the next iteration, he or she might not. So since the payment domain is always evolving, we wanted it to be as simple as possible, and we did not want it to impose any new burden on the developer. We wanted it to keep it simple and easy to use. So these were the challenges we had to also solve when thinking of any the solution for this.
So ideally, we want something like one issue is identified, it has to be solved systematically, and it should never repeat. And whenever we see a system, we always wanted to solve systematic, and we don't want to like revisit it again and again, and all the knowledge transfer and all. See, you even like we can like educate and all, but then there can be mistakes, and we cannot remember everything. So all those cases, if we put it on a more system, right, it will be like always followed. Even we don't have to like explain explicitly. So that was also like one of the thing.
So the answer to all our questions and challenges were like compiler level static checks. So a static checker is like kind of a tool which takes the source code, and it analyzes it, runs some validations on it, and then gives us the list of defects. For us, we could have used some external tools as well, but we wanted to not have any impact on like the compilation process or like some development process. So compiler static checks were the things which we came up with. So these are the rules like which there are some rules like which we can define in some file, and during the compilation itself we will attach a plugin to it which will take these rules, and it will perform the validations based on those rules. And if there is any error or violation for that rule, the code will be flagged with the exact location and the error it has. And this will give developers immediate feedback, and it will reduce the risk of bugs that in the code, like whatever we have identified earlier, we are sure that that bug won't be there again. We can think of it as a like a smart river which never fails to check the predefined rules. One of the benefits of this approach, I will say the key benefit of this approach is that it leverages the compiler generated data. So this compiler generated data can have like abstract syntax tree, like, and type information, including the domain type information as well, and function signatures it can have, and it will have like module dependency, like which module depends on what, and based on these, like we can apply the validations we have written. This allows us to like create some highly accurate chats without any extra overhead, because it's all about the compilation. We are just taking the compiler generated data and just processing it, so there is no overhead for like.
Yeah.
this compile-generated data?
Yeah, so this is generally the compilation pipeline, and if you see in this pipeline, right, the plugins are something you can attach this code anywhere in this compilation stage, and it executes, and then your code executes. So even if you want to throw error in that stage, right, you can still throw error. So we generally use compilation plugins mostly in type checker because we wanted to do that. We wanted to throw errors and like because we wanted type information in most of our use cases, like for example that show on a string or something, right, and maybe the enum check or anything. So most of our use cases revolved around type check, and that is why we wrote a plugin around type check only. Any rule that we can emphasize, right, we wrote that as a config so anyone can use it and inject it. So we wrote that, and such that it easily adaptable, and every repos can use it just with a config, and with any rules and all those errors, right, which can happen, which we wanted to prevent, which we wanted to enforce, right, all that we can write it as a plugin, and that is what we did. Yeah.
Okay, coming back to the domain safety, we built
Yeah.
two plugins, and let's see how they helped us enforce the domain safety issues we have discussed so far, and uh, helps us and improve the maintainability across the code bases.
Yeah, there was a plugin called Domain Checker that is ideally for like in a payments ecosystem. When we don't get a proper status back, we don't want to mark anything without any validation. So there was, if there will be a default state mentioned for an every time, and if you don't know the reason, you have to mark to the default state, and you should not mark any other state in any of the other enums, because enum check and all those things Haskell itself provide. But on top of this, we also wanted to this check that this particular enum is only selected for default and not any of the other enums. If you have validation, then right, because when this is getting thrown as a compilation error, right, even the devs will think, oh, okay, it's my bad, I should not write this as a default rule, then this is not the default state, let me go and revisit what is the actual failure state, let me go through the documentation, or let me go through that and then write a check rather than randomly writing a failure. Let me do some validation and then mark it as failure. If I don't know, let it mark it as default. So all those things, right, all those validations, even it will not allow devs to make these kind of issues. Yeah.
Okay, the another plugin we built was the Sheriff plugin. It was more of a generic plugin, like it was not tailored specific to the payments domain, but it was having some domain rules enforceability as well. Like the Sheriff acts as a code inspector for us. Like this plugin also, like we have built on the type checking phase only because we want to make it generic. And in Sheriff we have added support to check the unsafe functions, like whatever there are unsafe function, like we have talked about the head, and there is another function from just, which is like which can also throw errors at current time. So we have added this functionality to detect such functions uses across the code base, and without manual checking. Also we have added some deterministic infinite recursion. So basically what we do there is like if a function is called with the same arguments without any modification, then we are sure that it will be like our infinite recursion, because in Haskell the variables are immutable, and if there are some possibility of creating a mutable variables, but that is also avoided. So we also detect infinite recursions that way. Also for the slow DB queries issues we faced, we gave this plugin the metadata, which contained like the name of the tables and the index columns actually we have in the database. So now the plugin takes this data and it finds in the code, like wherever there is a DB query, does it have the required index field or not, any index field or not. And for complex uh, indexes as well, like we have added that thing as well. uh, this saves the this saves us from like the getting the slow db queries in any future, like no dev can add it now without having the index column. Sheriff also provides ways to like block a function call within a particular type of argument, like we had talked about the show, and all those things like are also possible with the Sheriff. Also with the new frameworks, like we have like any framework we have, you can just give the type in the framework, types used in the framework, and you can say like no, don't use this type on that thing. And no, you cannot write a function with this function signature, like if it is using that type, there should not be no transformation on that thing. So those kind of use cases also are like covered in the Sheriff. uh, when we were building the plugins, we tried to follow a design philosophy. Like we wanted to make the things as generic as possible and as flexible as possible. So we made the plugins adapted to the diverse need of teams we have. Like we first of all, like we kept the rules in a YAML file. So uh, any team which doesn't need a check can remove it from YAML file, and the teams needing new checks can add it to the YAML file. There is no need to just go and change the plugin. The plugin will take care of all these things if you are configuring the rules, and the rules are like pretty simple to write. And also we uh, allowed the fine grained control over like when to apply the rule and when not to. We gave them the facility to mention the name of the modules they want to apply the rule on. Also they can like just deny some modules, like don't run the check on these modules. And further going on, they can like exclude some specific functions as well. Like you can say like no, don't run on this function. This function is designed to be that way only. So we can like specifically exclude that function from the that list. Also we made we were having the we made it plugin first for the GC 8.10.7 and then added compatibility for 9 to it as well. And if someone wants to like contribute, they can add compatibility for the latest GC versions as well. Also the plugins are designed in such a way that adding new functionality to the plugin itself. Like suppose for now we have some things we have implemented, some type of validations we have added, but there might be other use cases that might arise in future, or someone wants to add according to their use case, like that doesn't comes under the current patterns we have observed and we have implemented. The plugins are designed in a way like you can easily add them to the plugin without much hassle. We have provided some generic helper functions to get the suppose you have some function name, you want to get the type of it, you can get it any phase. We have implemented the generic function for that. So these kind of generic and extendable features we have added to the our plugins.
Sure. So this is how we explored compiler plugins and added static checks towards it. Yeah, like now if you have any queries, we can.
Okay, so I think right now nobody has questions. So thanks a lot. Thanks everybody. Thanks Piyush and Chaitanya especially for sharing this wonderful information with us, and apprising us of the challenges that are there in Haskell and everything. Yeah.